In the earlier tutorials, I kind of went over just starting a batcher, and we started setting up some of the code. I just decided to start a new project. I'm going to copy that code into it so I can actually give it a name and kind of structure it more in the way that I want. So what we'll do here is I'm just going to pick one of these. I could pick this one. I'm going to pick this one this time. And I'm just going to call it, I don't know if it's a good name, I'll call it Galactic Frenzy. Just quickly here, I've gone over in previous tutorials the input class. I'm not really going to go over it here, but just for anyone who's just starting with this tutorial, I'll just briefly mention that we got this input class. You can check it out in other tutorials. Basically just captures the old and new keyboard state and does the same thing for gamepad. And we can just use this to check to see if a key is pressed or down. And in our update, we have to call update to make sure that it's getting the old and new state. There's also this escape. Like I said, I'm not going to go over it in this tutorial, but there it is. I'm just going to change the namespace for it to be the same as what we're using right now for namespace. So that way I don't have to add using. You can do it either way if you want. I added this public static right here for our random, and then that way we can use random anywhere we want. And I just gotta say using system here. Okay, and I made this shortcut to the graphics device. We went over all of these earlier. We got the backgrounds, the sprites, rectangle source for shots, flames, explosions on the sprite images sheet. I'm going to use a vector 2 to control the X and Y scrolling of the backgrounds. Some of these might be used from different classes. I think I can get away with using the shot and the flame just in the game one here. I'm just going to keep everything simple instead of doing too much organization. Explosions though might be handled differently. Maybe I'll put these up here and say public static. I think I already know what I'm going to do with that. Keeping all my public statics together. Actually, I prefer not to use very many of these. So double clicking on content here, it's going to add in a couple folders. Call this one music, add in a folder for sounds. I'll just call it sound. We could do the same thing with art, but since this is just a simple example, I think I'll just keep the few sheets of art in here. It's not going to be overly complex, so I don't need to, I don't think I need to keep that separate. I'm going to right click and I'm going to add from the previous one. As I mentioned before, I got these art assets that are matching, well, this one and this one here will match the screen size, screen resolution that we're going to use. And these are wrappable backgrounds, which will be important. And these are going to be the images we're going to use. I started making this QuadEffect. We'll just go into that real quickly and I'll explain how it works fairly carefully. If you don't have a QuadEffect started yet, if you right click on here, you go add a new item and click on sprite_effects and give it a name like QuadEffect and click OK. And so what you'll end up with is this code that's already generated for you. This is just telling it if we're compiling it for an OpenGL compatible project, which shader model and which shader models to use for the vertex shader and the pixel shader. And if we're making a DirectX 9 compatible version, it would be like this. This could be, if you wanted to add more instructions and do crazier things, you could change this, for example, to 5.0. For both of these, we're going to stick to DirectX 9 compatibility. We're not doing anything overly complicated here. And you should have something like this. If it's not the same, you could just make it the way I got it here. I actually erased everything and just typed this in. So I'm not sure exactly how close it is. I think the only thing I kept was down here, which is technique sprite drawing. Vertex shader equals compile VS shader model main VS. So whatever you call your technique here, you want it to match up with the name of your actual vertex shader. If this was blob vert shader or whatever vertex shaders you wanted to have, you can have multiple in a file. This would have to be the same here. As long as these match up, you can call them pretty much whatever you want. Same with the vertex shader, or I mean the pixel shader here. So to add textures, we can create a texture like this. I'm not even sure 100% whether this is even necessary to put this here. I'll probably even get away with just doing this. But this is the way I usually see it set up, so I'm just going to copy that. And what you do need though is this sprite texture sampler. And you could call this, again, whatever you want. You could call it text sample, sampler. And then in here, texture equals, and again, you can call this whatever you want. We could call it blob texture or blob text, or just, you could even call it texture. But you just got to make sure that if you're passing parameters and you have more than one texture, instead of saying text 0 is equal to this, you actually want to use the parameters, and I'll show that later. And in your parameters you would actually specify this sprite texture in quotes so that it passes that texture into this. For doing the world view projection, which is going to be used to manipulate our vertices, so any vertices that we have, if we need them to be displayed in front of the camera correctly, this matrix holds all those transformations, like the viewing transformation, world transformation, and the projection transformation. I added this int use texture here, which will act like a boolean. So if this is 0, it'll be false. If it's 1, it's true. And we can set that if we want. And then in the pixel shader, what I do is I set the texture color initially just to be a solid white. And then I say, so I mean that way, if you pass in a color and there is no texture, so if you use texture, it'll just sample it from the texture map using the texture coordinates to get it from the proper source rect location on the sheet. And then it'll multiply that by any colorization that we've added. Whatever color we wanted the sprite to be, that's multiplied by that sampled value. So if we just give it white, all 4 channels will be 100% multiplied by the RGB and alpha of this text color. Keep in mind that it has to be non-pre-multiplied if you want to play around with this alpha. Otherwise, you have to pre-multiply your alpha effect into your color. I'm sticking to non-pre-multiplied to avoid any confusion. So yeah, if it was set to not use a texture, obviously it would just multiply that solid white by whatever color. So if this was blue, for example, then the blue channel would, the red, green, and the other channels would be cut down to pretty much 0 if this was a solid blue, but the blue would stay at 100%. Just depends on how blue it is. If it was a bluish green, then maybe part of the green channel would be cut in half or whatever. That's kind of how the pixel shader is set to work right now, and I'm using this vertex shader output structure. You want to make sure that, because of the way the vertex declaration is set, you want to make sure that it matches up with that vertex declaration. So it's going to be expecting a SV position. Keep in mind too, when it's OpenGL, it's going to redefine that to be this, but that's already kind of taken care of here. So it's going to expect this 4 float position, which is a vector 4. I believe the W coordinate when it's passed in is going to have a 1 automatically in this case. Sometimes you actually have to put the 1 in your position on your own. You might want to double check that. But yeah, this is going to work fine for us. And the color is passed in next, and then the texture coordinates are passed in last. And you can see that I've matched it up to be the same way as in the inputs for the vertex shader. So the first thing that's going to happen in the pipeline, well, I shouldn't say it's the first thing, but the first thing that we care about, that what's going to happen in the pipeline, is this vertex shader here is going to get each of the vertices, and it's going to get their position, the color that we've assigned to them, and the UV coordinate or the texture coordinate, which is where the source rectangle, like the points on the sheet, and that's in normalized space between 0 to 1. Create this output here, which is going to hold this information that we're going to pass to the vertex shader. And I take each vertex and multiply by the matrix transform. That's the worldview projection matrix, which has all those transformations in it. And that gets the vertices to where they should be on the screen. And we just pass along the color to the vertex, or to the pixel shader, because the vertex shader isn't going to use it in this case. And we pass along the texture coordinates, same deal. And we kind of already went over how the pixel shader works. As it's interpolating across each triangle, it's using this sampler right here, this text2D sampler with this sprite texture sampler, which is basically just telling it which texture to extract from, to sample from. And it's just using the UV coordinates. So it's interpolated the UV coordinates. So this isn't one of the corner texture UV coordinates. This is somewhere in between while it's interpolating. We did kind of cover the theory about how the vertices and indices are used with the texture coordinates to extract across a texture. Basically what that sampler is doing is it's interpolating across the triangles and sampling from points at various points. And it kind of does it in this sort of scanline type deal, except does perspective correct texturing. So basically it'll be sampling here, then here, then here, then here, and here, and it'll go across, do another row, and it's just figuring out where it should get it from on the original texture using the UV coordinates that it's interpolating. If you colorize it, for example, give this that you just want it to be mostly green in this channel, mostly blue or purple in this channel, apparently mostly purple in this one, mostly red in this one. It'll smoothly blend between the two. If all four are the same though, then it'll be the same color all the way across. And if you used 100% white for all of them, it would just be 100% the original color channels. In this example, I think I'm just going to stick to sort of hard coding the width and height. We could make these into like a screen width, screen height variable, but I think everywhere I'm just going to assume that these dimensions will never change, but that's just for this example. For now, I'm going to leave is full screen as false. Until we're sure everything's working good, we can change it to true after. We're going to have to set up this random. So in initialize, I'm going to say random is a new random, so make sure to add that. Got a reference to the graphics device, set up the sprite batch. You can refer to one of my older tutorials to find out what these are. It's essentially a screen scale X, screen scale Y. So it'll scale the mouse coordinates. They match whatever resolution you're using. In this case, we're not using the mouse, so I just pass in 1, 1. Here I get the rectangles for the explosions and the flame on that sprite sheet. So that's just the coordinates of these. I'm just assuming that we'll extract from the same height and it'll move over by some horizontal offset. So in this case, these are moving over by 64 in each one, and that's why I can do that way. So you'll see here if I grab anywhere, if I go from the bottom right and up to somewhere, the W and H will show the width and height, but then you'll notice in the info properties, it will show the top left-hand corner. So if you ever need to extract texture coordinates, that's an easy way to do it. As for source rectangles for the other images, I might add another class to handle some of these, like the boss and the ship and stuff like that. And then I'll maybe put the rectangles in those. So we can add that after. In load content, we're getting the far background, mid background, and the sprites. In update, we just got an escape after we do the input update. And in draw, it just clears the device right now. So we could go with sprite batch begin and just make sure that our images are loading. And we could try drawing one. We haven't allocated any memory for the explosions and flames. Better do that before we do this. Okay, so I added these two lines. Now if I put F5, it should be okay. Nope. What did I do wrong here? Yeah, I just hit F5 again and it worked the second time, so I'm not sure what happened there. Maybe it just didn't build it, just tried to run it. Okay, so we're going to make a quad batcher. That's going to work a lot like sprite batch, but give us a little freedom to make customized drawing methods for like distorting the sprite or changing colors for each vertex individually, or even doing 3D rotations. We'll also be able to choose whether or not we want to use a 2D camera or a 3D camera. So we'll go over here and add that quad batch class. I'll just call it quad. I'm not sure what all I showed before. I'll just quickly kind of go over some of this. This is going to be the vertices that we're creating on the fly for each batch that we're going to render. These are the indices of the triangles. These are the vertex buffer and index buffer, which will transport our data to the hardware. This is how many vertices are in total after all the sprites have been created, so all the vertices that have been added to this here. We got our default effect, which is the one that I showed earlier, and you can pass in an effects for a pixel shader, vertex shader, or both that will bypass those. And then we got our textures. I included old texture here in case you wanted to just store a texture and then restore afterwards to what the previous texture was. So I'll show that in a bit. And this is basically just for setting that matrix transform that's going to be used by the shader to transform the vertices in the vertex shader to their appropriate coordinates. In the case of 2D, the world and view will usually be an identity matrix. However, as I probably already mentioned, we can adjust the world for unique forms of panning or for doing a camera shake or something like that. But it's mostly the orthographic projection that we're going to use. In the case of a 3D camera, we'll be setting the view matrix, an eye position and a target position to do an inverse transformation so that everything's oriented around the camera as though it's looking from the camera. So it's almost like a world transform that's backwards to get everything within the camera's view. And then 3D projection matrix. And that's all going to be combined into this matrix, which is sent to the hardware. This normalized U and V, I think I went over that already too. And that we can multiply any source rec coordinate by that, and that'll get it so that those are some percentage between 0 and 1. And the hardware will then be able to use those UV coordinates for interpolation. We've got our blend state. We can keep an old blend state if we want to switch back to what it was. Sampler state, depth stencil state. These two won't change very often. Sampler state, we might change that actually once in a while for like wrapping or what quality sampling, for if it has dithering, or point based, or nearest I should say, for blending the pixels basically. So if it's linear, it's going to make it smooth. If it's anisotropic, it's better for 3D, so it's really smooth. We're going to keep the screen size data, that'll come in handy. Anytime we want, this is why I gave public access here, anytime we want, we may want to change the Z value of what we're drawing. And we can do that on the fly as we draw. Technically, when you're drawing, you're not drawing, you're basically storing vertices, but you can store them at the depth value you desire as you go. And then when the end comes, call to the method end is going to draw everything all at once that's been stored in these vertices up here. See, keep effects. I just decided to add this option, keep effects, and what that basically will do is if we hit an end and start a new begin, we don't actually have to pass in the effect. It'll just keep the one, if this is set to true, it'll just keep the one that the custom one that we had set, and it won't set it back to null. So normally between a begin end pair, it'll set it to null when you do a different begin end pair, unless you pass in the effect. So this way it just makes it so you don't have to pass it in again if it's going to be the same effect, but at the same time too, we don't want to assume that they're going to keep the same effect between each begin and pair, so it's best not to do that. So that's why we do this sort of thing. Okay, so let's go up to the top here and just let's make sure to add these in here so that we can set a reference to the GPU. So anytime we need to use it, we can. And we'll have a Boolean called began. And what that does is if begin is used, then began will be set to true. And then when end is called, it'll finish with began is equal to false. So if you were to try to use an end and there has been no began, it'll be able to send a warning. If you didn't have your begins and your ends paired correctly, that'll help you to debug that and know that something's wrong. So I added this constructor here, and I'll just quickly go over what this does. So we have to load in our QuadEffect that we created earlier, and that gets put into default effects. We get that reference to the graphics processor, the graphics device, and we'll store the width and height of the screen or resolution of whatever it is for our viewport. You might actually want to pass these in depending on what you're doing, like if you're using specific render targets or something. We allocate some memory for 2048 quads or sprites. Here we're just storing the indices in a static buffer. This is the static buffer here. I believe I actually did go over this already. There's 6 indices per sprite because for each triangle, there's 3 indices to the 3 vertices that are needed. And since there's 2 triangles, that makes 6. And there's 4 vertices for each sprite. So I think I actually already mentioned that, and I mentioned about why we're using an index buffer and that it's a little bit more optimal. So we got to make sure we set the world matrix to an identity. We can optionally pass in true, and that will cause it to call this set 3D camera, providing the center of the screen and some distance away from 0. So I put it at -900. And this here is going to be the forward direction. So I'm going to have 1 being the forward direction. If I had this at, say, +900, I could put this at, say, -1. That's just the direction the camera is looking. Set 2D camera is what it normally does. And then we set the default states for the hardware. And right here, technically, we're not actually setting those states. We're just storing what we want to set those states as. So we're just storing the values. I'm defaulting to alpha blend. Probably actually, based on my taste, it'd probably be better if I had that set as dot non pre-multiplied. And linear clamp for the sampler state. No depths being used by default, but you can change that to true. Rasterizer state, call none. No matter which way the geometry is facing, if it's clockwise or counterclockwise, away or toward the camera, it won't matter. It's just going to draw not. If we used counterclockwise, any polygons that are facing away from the camera will be culled in the hardware and they will not be drawn. So if you were to make the polygon a single polygon face away from the camera, all you'd see is black, or you'd just see the background. That becomes handy when you want to reduce the number of polygons it has to try to interpolate through. And in our case, all our polygons are facing towards the camera, which is why we can say cull none, because it's not going to matter. I set the default depth to 20 as the Z value. Actually, let's make this camera specific so that we got, say, 0.5 as the depth value if we're using the 2D camera, and then maybe 20 if we're using the 3D camera. Okay, so I just added the camera code here, and with the call for a 3D camera here, I'm setting this to 1 and putting the camera at -900. So 1 is the direction, this is the position here. So that actually calls this one here, where I set the position. And for the target, it's going to pass in this vector, which is composed of the XY of the camera's position, and then just some Z value for what the target is. Technically, rather than a direction, this should actually be a depth value for, or I should call this target depth, or target Z, I guess I could call it. So now in set 3D camera, we can get use the eye position and the target position that we created here. I mean, if we wanted to, we could also just call this one here and supply an eye and a target position. I just wanted to provide another overload to make it easier to set a 3D camera if we wanted to at any point. So we gotta set a viewing matrix. We can use this matrix.createLookAt, supplying the camera's position, the target position, and a vector determining whether -1 is down, or I mean, whether -1 is up or if +1 is up. So if you go like this, you can see the camera up vector right here. And what this does is it'll transform everything around the camera as though the camera was at 0 looking down the Z-axis. So it's transforming the world around the camera. I kind of explained that already, so I'm not going to try to explain that again, but in previous tutorials, we already went over this, creating a perspective field of view. I'm using pi/4. That's 45 degrees, I believe. If we wanted, we could say pi/2. That'd be 90 degrees. It just depends on what kind of field of view you want. And I'm just getting the aspect ratio from this viewport here. If we passed in a screen width, screen height, like a custom render target or something, then we could just use these, where we'd say some aspect ratio is equal to height over width, I believe. That's what we would then use right here in place of that if we wanted. We want to set a near plane distance. Make sure not to set that as 0, so I put it at 0.1. And a far plane distance, so any geometry beyond 2000 in depth from where the camera is will be clipped. You can optionally offset pixel, or offset the graphics by half a pixel for when it puts it on the screen. I did that by creating this half pixel translation, -half a pixel, and factoring it into the projection matrix. Because of the order of operations here, this will translate it by half a pixel, and then this will effectively provide our projection adjustment after. So here I combine the view and projection into one thing. So for example, if we're not changing the viewing matrix or projection matrix very often, but we are supposedly perhaps changing the world matrix often, we can just multiply world by view projection the same way we did here, and it'll be a little quicker than trying to multiply all three. And here I'm setting the default depth value for each vertex that we create to a depth of 20. So you can adjust that as you please, and you can even adjust it while you're drawing so that each sprite or item is drawn at a different depth. For the 2D camera, we can still provide depth values, but we're not going to get a perspective projection. It'll all be orthographic. And our depths will range from 0 to 1. For this orthographic off-center, we want to actually reverse this to, so let's say like -100, for example, 0 to -100 for the orthographic off-center. And the reason we'd want to do that is because we want to flip everything so that our resulting depth will range between 0 and +1. But I think otherwise it might end up being 0 to -1. I found I can get away with pretty much anything I want if I go -2000 to 2000. see here. There was some reason I was doing this, and it had something to do with rotating huge objects around 0, and I wanted to be able to see it from both sides properly. So this just depends on what your needs are, but I mean, normally you can get away with doing something like this. So I'm adjusting this by half pixel. Again, same sort of idea. Keeping the view projection just in case those don't change. Viewing matrix is probably just going to be identity anyway. And multiplying by the world matrix here, which is probably going to be identity to start with. In fact, it is to start with for now. So you could even get away with saying world view projection is simply equal to projection, at least at the very start of your quad creation. And then I'm setting the default draw depth, so the vertex position Z value as 0.5 for anything that we're drawing. I got this public method here where you can, if you want, change the world transform, and that'll come in handy if we don't feel like passing it in the begin. We don't feel like putting in all the parameters just to get to the part where we say we want to change the world transform. We can just use this, and that'll update the correct matrix transform to be passed to the shader. Next up will be our begin method. I put this reset begin in here just to try and reduce the amount of code in my overloads for the begins. So essentially when begin is used, we can pass in the texture, which we will extract all our sprites from. So we'll kind of have most of our sprites on one texture most of the time to improve efficiency. I prefer this method over sorting textures, and this way we'll make sure that we're manually using our texture switching in the most efficient way possible. If not reset begin, it returns, so that means something went wrong. Probably something right here, like if began. So we called begin, we didn't call end, then we called begin again, and it'll provide a warning saying that began was already called and there hasn't been an end since then, so it's going to notify you that and return. Then we make sure we reset the vertex count for this batch of vertices. We're starting a begin, so we're going to say began is true. If we're not keeping the effects, which is the default behavior, then we're going to set effects to equal to null. And in one of our begin overloads, we'll be able to pass in an effects. And then after that, for example, if we want to keep the effects, we can publicly access this keep effects, say we want it to be true. And then when it calls other begin end pairs, it'll keep that effect running. It won't set it to null next time it comes into reset begin. I got this for setting the texture coordinates. As I said before, we need to normalize our texture coordinates. So I create these multipliers that when multiplied against a source rect position, it will get the percentage into that texture. So some number between 0 and 1 using the texture width and texture height. This set text chords. Actually, I should probably just change this to text chord setup because we're not actually setting texture coordinates technically. All right, we're going to make sure we got our texture and we're going to set that up. I'll add some more overloads here for other things we might want to do for our begins. I added some more. We looked at this one already. This one just allows us to do a begin end pair where the only thing that changes is the blend state. So we're still using the same texture. So this just resets the vertex count as we've seen up here. It resets the vertex count. Make sure everything's okay with the began. If we want, it'll reset the effects to null. So basically we're just changing the blending state, and it'll actually set that on the device when it calls end. So that way we're doing all the device changes, texture changes, passing parameters to the hardware. All that stuff's going to be done in the end call, and that's when it's going to draw all our polygons. The next begin overload I got here, we can pass in a texture and a blend state. So it does the same thing the other two did, except it allows us to set the texture and the blend state. And this one's the exact same thing, except it allows us to also add that we want to change the sampler state. And again, this one is the same, except now we're also adding the depth stencil state. And I got another overload here, which is actually going to call this one here. It's just a little more convenient because we don't have to specify anything as far as an effect goes. Actually, I probably don't even need this one, right? Yeah, because I can set this to be null as a default value. Okay, so the exact same thing as above, except we add in, because we got this matrix world here, and this possibly a myEffect being passed in. If the myEffect is null, then we set our custom effects to be myEffect. And we also update our world transform that we passed in. Okay, so up next I added this switch text. And it basically acts like a begin, which just changes the texture and retains the old texture and blend state. So that way when you call restore text, it's going to restore it to the previous setting. So I made this overload just for switching the texture, and this one this one's actually for switching both the texture and the blend state. These also call end, which we haven't made yet. And our end is going to render all the vertices we've created so far. Well, we haven't actually set up any of our vertices with any draw calls yet. That'll be these vertices here. But we're going to make some draw calls after I make this end method here. So let's just start making this end method right now. Okay, so some of this code I actually pasted from one of my old batchers, and I'm just modifying it a bit in a way that I think is a bit better than the way I had it before. All right, so when we call end, I have this warning if begin hasn't been called already, so that would be kind of necessary. So it returns and provides a warning for debugging. If the number of vertices is greater than or equal to 3, if it's 2 vertices, something's wrong, so that should never happen really. But I mean, I guess you could have a begin end pair that are empty, in which case it'd just skip over this, say begin as false, and reset the vertex count to 0. Now, in the begin, we've got this reset in here, and it sets the vertex count to 0 anyway, so that is a little bit redundant. However, if we're drawing and we reach the end of the number of sprites we're allowed to make, I can call end from the draw statement. Once it's reached a full batch, it'll call end, it'll reset the vertex count. Now it will set begin to be false in here, but when that happens, when it comes back to the draw, it'll switch the begin back to true again. So I'll show you that in a bit, so you don't have to worry about that. So here we're going to set the device states, the blend state, the device, like graphics device, which in this case we're just calling it GPU. So we're setting the blend state, depth state, stencil, sampler state, how smooth we want everything. And if the rasterizer state call mode is not set to none, or have it programmed to automatically set it to none. If you don't want this behavior, you can comment that out. You might be doing 3D, and for some reason maybe you have billboards that you only want to see from one side, or maybe you're actually doing 3D with these begin end pairs. This is possible, in which case you may want backface culling to be turned on so that faces of polygons facing away from the camera that are behind objects, or on the back sides of objects, for example, those will not be drawn. There'll be no attempt to render those, which is a little bit more optimal. So in our case, I'm just going to have it switch to call mode none so that it doesn't have to do those dot product tests, since we know all the polygons should be front-facing anyway. And we're gonna call our default effect, or apply our default effect here, which is that shader that we made. So when it sets that effect, it'll use this vertex shader and this pixel shader. And if we want to send in a custom effect, if it's just a pixel shader, it'll just automatically ignore this one and use the new one. If it's just the vertex shader, same sort of thing. And it could also be both if you wanted, and it'll just replace these with the ones that you sent in. And that's effectively what this line is here. If the effects is not null, instead we apply the technique that's in this effects, whichever technique or techniques are there. If the texture is not null, which it shouldn't be, however, if it is, we can set use texture to be false or 0, and that way our shader knows to just use the color white and just colorize it using whatever color values you were using for vertices. So we set our texture, and keep in mind this only works for the first texture. If you're using your own shader, the best way to do this would be similar to this line here. What I mean is, instead of having that, you could pass to it sprite texture, or whatever the name of your texture is, and then here whatever the texture is that you're passing in. If you have more than one texture, you'll want to make sure to do it this way, otherwise it won't work. Like you can't do that, for example. You can't say 1. You can get away with it if you do it for 0, but you can't get away with it for any beyond that. Here we're just calculating how many triangles there are. So 4 vertices per triangle divided by 2 gives you 2 triangles, and that counts up the number of triangles based on the vertex count. When we make our draw methods, we're going to be adding vertices and adding to the vertex count each time we do that. So that's how we're going to end up with this vertex count and the vertices. Since we're using the draw user indexed primitives method rather than just draw indexed primitives, we don't have to set the vertex buffer and put these vertices in there. This right here is going to do that for us because it's the draw user indexed primitive. So it does that inside on its own. And this will set the vertex declaration type. So in this case, we're using vertex position color texture. And you'll notice there's other types here, like for normal texture or just position and color. And we can create our own vertex declarations too, if we wanted to. Let's see, so here we got the starting vertex offset, which is going to be 0 because we're going to span across all of them, and the total number of vertices. And here we're just passing in the indices that are technically already on the hardware, and index offset in case we just wanted to span a certain number of indices. If, for example, I wanted to draw something that's halfway into our index buffer, starting at index 500, I could type in 500 here, and then this would be however many triangles it would be for that model that spans that section. So the usefulness of being able to do this is if you wanted to have a whole bunch of models and you didn't want to pass them all individually with a bunch of different calls, but you wanted to only draw certain ones in a certain frame, and you're keeping all of them in a vertex buffer, all of them in an index buffer. It's especially good if it's a static vertex buffer or static index buffer, because you can tell it, I just want to draw this section of indices, whatever it starts at, however many triangles there are, and it'll just draw whatever object that would be. And that way you can keep all of your vertices and all your indices all in one big giant vertex buffer and one big giant index buffer, and minimize transfers that way. Okay, next up we'll add this. Just wanted to start off with a simple draw technique to kind of give you an idea of how we're creating those vertices. So I allow the specification of a destination rectangle, that's some rectangle region that we want that sprite to fill on the screen, with the option of changing the colorization of it. So if we wanted it to be partly see-through, we could give it a color with, say, half transparency, something like that. If we wanted to make it reddish, you know, have 100% for the red channel, a lower value for the other channels, that sort of thing. So the first thing we need to do here is store the upper left coordinate, which is destination X, destination rect Y. So it's the top left corner of the rectangle. Here we're getting the right side of the rectangle on the top. That's upper right. And we do the same thing for the lower right and the lower left. So you'll notice we're going in a clockwise manner. So what we do is we save vertices, the current vertex count dot position is equal to that coordinate using this Z value here, this depth value, which we originally set in our set 3D camera or set 2D camera. And since it's public, you can change it on the fly if you need to. So anytime before you call a draw, you can change the Z if you want. And then we set the texture coordinate. In this case, we know it's going to be the entire texture that we're drawing to this destination. This is just a very simple version. It's not getting it from a source rect. And so I just supply the top left corner, the top right corner, the bottom right corner, and the bottom left corner. Again, going in a clockwise order. Based on the indices, it'll go 0, 0, 1, 0, 1, 1, and then back to 0, 0. The next three indices would go 1, 1, 0, 1, the bottom left, and then back up to 0, 0. Oh yeah, I also set the color here. You notice that each time I'm going vert count plus plus. So that's kind of important. We need to add up our vertices correctly. If our vertex count buffer gets full, then we can call end, and it'll go through here, draw everything, reset the vertex count to 0. Now keep in mind it's also going to set began to full, or to false I mean. And when it returns, we set began back to true because we're technically not done yet. And that way it'll start over in filling up these vertices. And some of them are already drawn into the back buffer. I'm just going to scroll up a bit here. And in here, I'm going to add another draw dest. So an overload that does it a little bit differently, gives us a little bit more options. Okay, so I added another one up here. And I say stretch a source image to fit into a destination rectangle, allowing for color blending. So this is essentially the same thing, but it allows us to specify a source rectangle to extract our UV coordinates from. So that's where on the texture map it's getting the image. And we can also supply 4 different colors if we like. So first of all, I set a width and a height to be the source rectangle's width and the source rectangle's height. I get the destination coordinates exactly the same way we did in the other one. This time I get UV texture coordinates, and the way I do it is I take the top left, top right, bottom left, or bottom right and bottom left, and each time I do that, I multiply it by this normalized U, which we calculated up here to be 1 divided by the texture width and 1 divided by the texture height. And what that's going to do is it's going to make the texture coordinate be somewhere between 0 and 1, which is what the device wants. If we've specified a sprite effect, a flip, to be flip vertically, in this case I'm anding together flip and this flip vertically because you can combine multiple flags. This is a flag type. You can OR them together. We might go into that in our example. If that's not 0, meaning that this is in here, then we can flip the v coordinate in this case, because this is a vertical flip. And the way we do that is we're just swapping the bottom one with the top one. And we do the same thing for horizontal. We switch the right and the left. And then we do the same thing. We just add in our vertex information, and that's basically it for that one. Again, same sort of thing. Call end, set begin to be true if it fills up the buffer. All right, let's go up on top of here. I'll add in another overload. And since all this does is call this method here, except supply color 1 same for all the vertices. That way we only have to say color 1 here. We don't have to supply color.white 4 times if we're not using a different color for each vertex. And since this is all I'm doing here, I added this method implementation, options, aggressive inlining. Hopefully what that'll do is it'll substitute basically calling this directly instead. So instead of calling this method and then calling this method, it's just going to directly do this. Just makes it a little bit faster so it's not passing parameters twice. Okay, so up above this, I'm going to add another simple draw method, and we'll make one that allows us to just supply transformed coordinates around an origin. This is good for bone animated sprites. So I'm just calling it draw transformed vertices. Draws a sprite quad from 4 vertices, offsets from a position. So some location on the screen, you can have -10, -10 being top left, +10, -10 being top right, bottom maybe +10, +10, that sort of thing. And you'd supply those in these 4 vectors here, and you'd supply the position that they're centered around here, and a source rectangle to get the texture coordinates with. So that's where on the image you want to extract the image from. So to get those 4 positions, all I'm doing is adding P1 right here to this position. So I'm adding P1 plus position, P2 plus position, that sort of thing. The UV coordinates, it's the same sort of thing as before. And, you know, top left, top right, bottom left, clockwise order. And we're multiplying again by normalize U, normalize V, normalize U, normalize V for the top left. So yeah, actually this is the top left, this is the bottom right. And we just use U1, V1 here, U2, V1, U2, V2, U1, V2 to kind of get those to where they should be. And again, this is for flipping them if we want to use flip horizontal or flip vertical. We're just swapping those values. Okay, and this is all pretty much the same. Since it's just using one color, I put C1 for each of the colors here. You could make a version of this too that would allow you to have 4 different colors. So let's scroll down under this between that one and destination draw. I'm gonna add another one. This is probably the sort of thing you're waiting for. This one's just like sprite batch, but instead of supplying a texture here, we just supply the source rect. The texture's already been specified. And as I mentioned, if you wanted, you could make a version that supplies textures, keeps a list of textures, sorts them by dictionary or something like that. I'd prefer not to do it that way. I just prefer to keep all my textures on one sheet if possible. And switching with a few begin-end pairs is no big deal. So what you might notice here is we can specify a position, an origin, that's where it's going to rotate around. And that's a relative to the top left corner type origin. So if the rectangle is 20 wide and 20 high, you want the origin centered. So it'd probably be 10, 10, something like that. This is a vector 2 for the scale. That'll allow non-uniform scaling, so we can change the Y scale or the X scale the way we want. A rotation amount and a single color for this version, and so the C1 will be the same for each of these vertices down here. If the scale value for X or Y is not 1, then we're going to go ahead and calculate a version of the width that's been scaled and a version of the height that's been scaled. So we just take the source rectangle and that width and multiply it by scale to get this W value. And we're going to use that down here in just a second. And we do the same thing for this H value. For the origin, we just use the supplied origin, but we're going to multiply that by the scale too, because we're scaling the W value here. We also have to scale the origin value, and you'll see why in a second. If we're not scaling them, then we just copy those values into W and H and OX and OY for the origin. Here we're just getting the positions, the top left, top right, and we're adding the W for the top right, and that W has been scaled, keep in mind. And the same thing for like the bottom right, the H has been scaled, bottom left, H has been scaled. So these will be the vertex coordinates. However, we may want to rotate the vertex coordinates. So if the rotation is not 0, we can go ahead and calculate that. To do this, we first must know the actual position that we're going to rotate around. And the origin is an offset from the corner. corner. So we take the top left position and we add that origin of value on, and we do that for the y also. We're going to store ahead of time some coast value so we don't have to keep recalculating it. And what that's going to be is the coast value for the rotation passed in, and we need a sine value for the rotation passed in. And you may remember from previous tutorials about how the rotation works, so I don't want to go too much into detail about that here. And to get the horizontal radius and vertical radius for the two vectors that we add together to make the rotation, for the first vector, the x-axis basis vector, we say that it's x1 minus OX. So basically what we need to do is we need to take this top left-hand corner, x1, y1, subtract it by this origin amount. So that's this distance between this origin, the true origin, 0, 0, and this OX, OY. So we want to subtract it by OX, OY for all of the coordinates, and that will effectively translate everything around the true origin, and then we can apply our rotation to those, and then we'll add it back later so it's where it should be on the screen again. So again, to do that, we've got to subtract OX, OY from each of these coordinates to get it translated around here. So let's do that then. We'll say that our horizontal distance is going to be x1 minus OX, and our VD1 vertical distance is going to be V1 minus OY. You'll notice too I put x2 minus OX here and y3 minus OY. Just to avoid confusion, I'll change this bottom right hand one to x3 and y3, but you'll notice here x2 and x3 are the same, so it wouldn't really matter which one we use. That's just to avoid confusion. I'll stick to x3, y3 for the bottom right. So again, if we're to imagine that this is already translated to here, the values that I'm getting would be a horizontal distance from here to here and a vertical distance from here to here to create the composite vectors, this one and this one, which we can rotate. And I'm going to do the same thing for the bottom right. I'm going to have a vector that goes there and a vector that goes there, which will be the other distances. So order of operations, the multiplications will be done first, which will essentially process our rotation, and then everything's added together after. So our translation is effectively done after the rotation. And this OX and OY contain our translation back to where we want it. So to get it from here to here, that's what that OX, OY value is, which we calculate here. So we're adding that position back in. But let's focus first on what's going on here. So that horizontal distance will act like a radius, like we're moving this around in a circle with the cos and the sine. The horizontal radius we use here, and the vertical radius, well, we kind of went over the math for how that works before. So with this math, we're effectively creating a composite of those two vectors. And you can see with the top right-hand one, we have to use HD2 for both HD2 for the horizontal radius and VD1 for the vertical radius. So like I said, we're composing those two vectors together to get the bottom right one, for example, horizontal to the right, HD2, and vertical downward, which is VD2. And you can see how we have to use HD1, which is horizontal left, with VD2 vertical down. This is for number 4, and same thing for the Y4. So we're adding those two composite vectors together to get the rotated position of those points. We get our normalized UV coordinates from our source rect, flip them if we want, and do the usual and create our vertices using a single color this time in the same way that we were doing before. So up here, I'm just going to add overload. So I added this overload again with the aggressive inlining, just so for the same reason mentioned before. And this version's the same, except we're allowing them to just specify float as a scale instead of a vector as a scale. Just a little bit handier, and it's going to reinterpret that with this aggressive inlining. It should reinterpret that you mean to do this, and it'll be a uniform scale that way. Now, it would be nice too if we didn't have to specify an origin each time, if it just automatically rotated around the middle. So we could make a version for that. We'll go down under here, and I'll just add one real quick. So we got this draw method, no origin, rotates around the center at a position, non-uniform scale. We can create an overload too for that, like we did above. Single color. So I'm just kind of making common methods here where we're not going to want to change the colors very often for the 4 vertices. So if you want to add a version too that does that, you can. This is exactly the same, and the only difference is that you'll notice in this one, instead of saying that OX is origin times scale, or that it's the origin, as an offset amount, what I'm going to do is I'm just going to get the origin based on saying width divided by 2. So W times 0.5 and height divided by 2, which is effectively what's going on here. Except in this case, let's see here. Oh yeah, I don't, in this case, like you'll notice up here, I had to multiply the origin x by the scale. Yeah, the reason I don't have to do that here is because the W and H are already scaled. So that scale's already been factored into the W and H when we do this, so we don't have to do it. And otherwise, if you look at the rest of it, it's all exactly the same as the other one. If we go up here, we can add some nice overloads to make things really simple for scaling, for example. So I added in 2 overloads. I added in this one, and I also added in this one because I thought this would be really handy too for drawing a full texture, assuming we want to use the entire thing, and we just want to draw it to the screen or something simple, where we don't really want to do anything fancy. Maybe scaling in the X and Y, and that's about it. I'll just quickly explain these two. So this is the same as before. We pass in a scale, and it's just going to convert it for us to be like as if we called this with the scale comma scale. And for the draw full text, allows us to specify position, X scale, Y scale. And for the source rect, it's just going to create one using the top left of the entire texture, the entire texture's width, entire texture's height. And that's effectively going to be calling this method here that we've already made. Also, it's going to assume that you want it 100% white. So you could put a color option in here too if you wanted to. All right, let's go down, and I think we're gonna add another one. There are times when you may want to draw some ice or some water or something where the transparency changes and the color changes a bit as it gets deeper into it. So it'd be nice to have the option to modify any of the 4 vertex colors, but also be able to just specify some simple parameters and maybe not any rotation or anything complex. All right, and so that's what I added here. Fast, a simple 4-color draw. Takes the source rect, position, 4 different colors. Nothing new so far. Width and height, gets the positions as we normally do. Again, normalized UVs, flipping if necessary, and then C1, C2, C3, and C4 for the 4 colors. And let's add an overload for this just to make things a little bit easier. All right, I added this overload. Allows us to specify just 1 color, source rect, and a position. Really, really simple. And it basically just calls this just at a position with the source rect. There are times too where you have a tree or something and you kind of want it to be shaded a bit darker on the bottom, maybe a little bit greener on one of the corners, and maybe you want to be able to rotate it with the wind affecting it, scale it based on and rotate it based on how you're building your level. And you might even want it to stretch and sway in the wind, so you want to be able to distort the 4 corners to give it a nice squash and stretch effect that's animated based on sine and cos or something. You can do all kinds of different effects on it. You may not necessarily need to use a shader for that. You can just use a distortion method. So let's make something to allow us to do something like that. Okay, so I added this draw color distort method here. Freedom to modify a sprite by shape and colors. Allows shape distortion, good for pseudo 3D, swaying trees, multiple color blends. There's a lot of different parameters that are passed in here. So I'll just make this into 2 lines. We've got our source. We can put it at a position. We can scale it. We can rotate it. We're going to assume the origin's the center just for the sake of avoiding that extra variable entry. If you wanted, you could make a version too where you could specify an origin. Like if you don't want part of the tree to rotate in the center, maybe you want it to rotate at the base of where the leaves are on the tree or something like that, or at the tip of a branch, or just depends on what you need. We'll also allow supplying a vector offset and 4 colors. So keep in mind these are actually vector offsets from the position. And again, if there's any scaling, then we get our width and height values as being the source rectangle width times the scale X, and same with the Y. And we don't have to worry about scaling the origin again because it's already done in the W and H. And then we just multiply that new width by half, or divide it by 2 by timesing it by 0.5. Same thing for the other one. And then we also want to scale the offsets based on whatever scale we're passing in. So here I'm getting the X01 or X01, Y01. Same with the other ones for the X02, Y02. Just multiply them by the scale amounts to get the scaled versions of those offsets. We want to know what the point is after the offset. So those are each offset from position. So normally when you pass in your v01, for example, it might be assumed that it's the top left rectangle coordinate. So that might be 0, 0. The top right one might be 0, the source rec width. Just depends on how you want to set up those vectors when you pass them in, and then you can add some kind of animation to those. So to get those positions, we're just going to say it's the current position that we want to draw it, plus that offset value. Oh yeah, the way I made this will be the offset from each corner actually. So if these were all 0, you'd still get the 4 corners, but if you add in some offset amount, it's going to deviate or move away from each of those corners by whatever amount you specify in your V1 to V4, which becomes the X0 to X01 to X04. So that's actually how that works. So I kind of explained that not quite right at first. I just have this comment in here too as a reminder that you can create an alternative and use an origin that you can pass in. But we're going to do it this way and just assume the center. So without scaling, we can just directly use the V1 to V4 that were added in. If rotation's not 0, then we get the offset X as being the position plus the origin. And by subtracting those, we get the offset to the 0, 0, where we can rotate around. So this is the same as before, where we set up these horizontal distance and vertical distance that we can use as sort of basis vectors. What you may notice different about this one is instead of preparing an HD1, HD2, that sort of thing, I'm just recalculating HD and VD for each one of these. You can see how that works here. UV coordinates are done the same way as before, and vertices are filled in the same way as before. And we got 4 individual colors here. Let's go back up and we'll add an overload here. All this overload does is it's the same thing. It's just calling this right here, and it's going to substitute this and just reuse the same color that we supply in all 4 slots. So that's if we just want to, we don't want to have to type in color.white 4 times. Alright, so the next thing I think we'd like to add, as I'd been kind of hinting at before, I thought it would be really cool if we added the ability to draw something, technically a 2-dimensional quad, but manipulate it with matrices in a sort of 3-dimensional way. So let's go ahead and make something to do that. Under draw test I added this now, so I got this XYZ rotation draw, so we can rotate around any of the axes. It takes a source rect, position, allows non-uniform scaling if you want, and rotation around X, Y, or Z axis. X being your roll, or no wait, no. X is your pitch. That's gonna turn your nose of your airplane up and down as you're rolling around the X axis. Rotation Y is going to be your yaw, that's back and forth, left to right. Rotation Z is rolling around in a circle around the Z axis. So that's how we're doing all our rotations here up above. It's all around the Z axis, so you're only rotating the X and the Y axes because you're rotating it around Z. And we can supply a color. I think this version I'm just going to have one color. We could make a version with multicolors if we want later. I started off by adding this here, which is different from the other ones because now I'm just saying upper left, upper right, and bottom left are going to be the vertices that we need to work on. If there is scaling, I'm going to multiply by the scale factor, X and Y, and the scaling's already factored into the width and height as before, and we're just going to assume an origin that's at the center. So we could also modify this to take in an origin, which would be some offset, instead of just going width divided by 2. This is the same thing with no scaling. If we did pass in a depth, I'm allowing this optional depth here. That's why I got this question mark. If this is null, so I made this nullable by adding this. If this is null, it'll just skip this line. But if it does have a value, it's going to assign that value to the Z. So it just kind of makes it a little bit quicker to add a Z value onto the end of this if you don't feel like specifying quad.z all the time. And you'll notice what's different here is we're using vector 3 instead of just floats, which contain 3 floats, but we can do vector 3 transformations with matrices. So we're going to put it in our vector 3 type, specifying the z on this right hand side here, and the position x being the left side. I'm pretty sure you understand all this. It's the same as before basically. Position plus width. Same with the height over here. To get the upper left, upper right, bottom right and bottom left hand vertices. And we want to get the local coordinates, so the coordinates centered around an origin of 0, which we can then rotate. To do that, I get this mid vector here, which is going to be a vector that's constructed of the x position, so the position of the sprite that we want to render on the screen, plus the origin offset. So it'll be the center of the sprite rather than the top left-hand corner. And what I'm going to do is I'm going to subtract that distance to that point from each of these coordinates here, so that all these coordinates end up surrounded, or I should say, so that all of these coordinates are centered around 0 and suitable for rotation. To create a rotation matrix that rotates around y, x, and z, this kind of matrix works on the basis of rotation as I described it in previous tutorials. It's just in a matrix form. So we don't supply x, y, z like we normally do. We supply it based on yaw, which is around the y-axis, pitch, which is around the x, and roll, which is around the z. And then what we can do is we can do a vector3.transform using this rotation matrix that we supplied here. So this here is a matrix on this side. And this will result in a transformed or rotated upper left-hand coordinate around 0. So to get it back to its correct position, we have to add this mid onto it. So we're translating it. Obviously, this operation will happen first, and then it'll add the translation onto it. And now we have our rotated version at the correct position on the screen. We do the same thing as before to get the UV coordinates. So that part's no different. And same thing with creating the vertices, it's the same as before. I just added these lines here, and what we're going to do is we're going to draw lines to indicate where our bounding boxes are. Or sometimes they're called hitboxes or collision boxes. And we can use those to show when we're doing a diagnosis what's going on with the collision detection, where the collision boxes are relative to the character. Sometimes you want your hitboxes smaller than the character. You don't want it bigger, obviously, because then sometimes bullets could hit your character even though they technically didn't hit your character. So just want to make sure that the collision boxes are in the right place. Normally we're specifying a texture and we're extracting from a texture. If we specify no texture, or texture is false, I believe I made that public, and if you look in end here, this will pass whether or not a texture is actually being used. In this case, if we wanted, we could say use texture as false and just specify a color, and it would draw the lines without using the texture. And it wouldn't matter what source rect you use because it's not actually using the texture anyway. So just to clear up that if it causes any confusion here, because here we're drawing using a pixel source, and by default it'll be 0011. So like I said, if there's no texture set, it doesn't really matter where it's extracting this from, it's going to ignore the texture source anyway. But if you are keeping a texture set, which is usually what I do, I usually have a pixel in my texture somewhere that's white, and I just assign this position here, this x and this y value, to where that pixel is on my sprite sheet. You just got to make sure you're using the right sprite sheet. So you might even have a different begin and batch with heads-up display objects or something, maybe some white pixels for drawing lines, that sort of stuff, and you can extract that here. So it's calling our draw function and using this as a source rect. And the start position, so this is the vector2 position that we're going to draw it, is going to be this start value that we pass in. The third parameter should be the fifth overload, should be origin. So this is going to be the center of that pixel. I'm setting it to the left side of the pixel, halfway down the pixel, and we're going to rotate around that point. The scale itself is going to be a horizontal scale of some length, and we need the length between end and start. So we get delta is equal to end minus start, and then we can use delta.length to get the length horizontally. So this would just draw a line starting at a starting position going straight to the right of some thickness that we provide here. By default it's 2. What we can do then is we can add a rotation value, and we can actually get the rotation value based on this end point and this start point using atan2. That's that opposite over adjacent thing. uses the delta y, the y difference, and the x difference, and atan2 to calculate the rotation. The atan2 is handy because it won't matter which of the 4 quadrants we're in, it's going to get us the correct angle. So we don't have to do any fancy tests because it's doing all that stuff internally. Now we got the rotation, the angle from 0. So normally you've got a line that's horizontal, and when you want to rotate, the angle changes in this direction. As you can see my cursor moving, it rotates in a counterclockwise direction. So this rotation value will end up matching up with the angle of the line that we're trying to create. So it'll take that horizontal line and it'll turn it around to face the correct direction and use the color that we supplied. Great, so I made another version of line. Instead of calling it draw line, I'm calling it line. I'm trying to make it a little bit like how it was back in the day when we were programming in BASIC, where you can just supply an X, a Y, another X, a Y, and a color. And that's all you really need. And then it does the same thing, it's just creating the vector 2s from those. I'm making sure, you'll notice in both these, I'm making sure that the pixel height and width is 1. If this is greater than 1, our scale here is not going to be correct. This is dependent on this being a width of 1. So this part's all basically just the same thing. So using these line techniques, I added this rect lines. Gets the top left corner here, top right corner here. You can specify color or thickness again, and making sure again that pixel width and height is 1. Instead of using these lines, because I mean I could make a version that draws using these lines, I realized it would be more optimal if I just use the same technique where I can draw a horizontal line by specifying here the position, origin of 0, and just scaling along the X or the Y based on the horizontal distance, or in this case, the vertical distance. So that's all we're doing. We're scaling either horizontally for the horizontal lines here and here, or scaling vertically for these lines. And that's all that does. That allows us to create a rectangle in the collision zone so we can see if we have placed our hitbox where it needs to be to collide correctly. So let's say we wanted to create a pseudo 3D game, or we wanted to just use colored quads. We don't even necessarily need to use texturing for like a 3D hilled landscape, like a pseudo 3D thing, or maybe we're doing ray tracing and we just want some basic colored quads and want to be able to supply 4 colors so we can get some nice blending between each quad. So I added this color or draw color quad technique, which can do that sort of thing. And you can even do a textured one too if you wanted, using the above methods. This is just if you want just a plain colored quad though. This one just takes our pixel coordinates, normalizes it to get the UV positions where it's going to extract from the texture map to make a plain color with. I mean, even in this case, you could modify the pixel value and actually just texture map it that way. Very simple. We just create the positions for our vertices based on exactly the positions that we supply right here. And same with the colors, color 1, 2, 3, and 4. So if we wanted, we could make the top 2 a light green and the bottom 2 slightly darker. And then when we create the next quad, the top 2 would have the other darker coordinates, and then these 2 would get an even darker coordinate. So it'll gradually blend to get darker and darker. Again, it just depends on how you want to do it. Like you can create pseudo lighting and do some pseudo 3D with this sort of thing if you really know what you're doing. The nice thing about this too is this doesn't have to be a uniform rectangle. This can be any shape you want, really. If we want to create a uniform rectangle and specify a rectangle, we'll just make something quickly for that. Okay, so I added this fill rect now, and the difference is you can supply a rectangle now. So otherwise it's pretty much doing the same thing. To get our vectors though, the P1, P2 to P4, we're just extracting the X of the rectangle, the Y of the rectangle, and then for the right side we're adding on the rectangle width, and for the bottom we're adding on the rectangle height, and then entering the coordinates and colors as usual. In this case we're just applying a single color and duplicating it across these, so that just depends on your needs. And that should be it for the batcher. The nice thing about this too is you can just keep adding things as you need them, or take things away if you don't need them for certain projects. So let's go back to game 1 and we'll test this out. So instead of sprite batch begin, we'll go up to the top here and we'll create a quad. So perhaps after sprite batch here, we'll put our quad batch in here too, calling it quad. Maybe we'll try drawing the far background first and see if it works okay. Before we do that though, let's make sure we go to initialize and create the quad class, or the quad object I should say. So let's make the quad instance, go like this, quad, pass in the content manager so we can load our shader and the graphics device, and we could say true if we want it to be a 3D camera. So we'll try both. Maybe we'll try 2D for now. Oops, this should say new quad. So I set the texture that we're going to use first in the begin, and the blend state, I'm going to make it opaque. Doesn't need any transparency because it's going to be the far background. And I'm setting it to linear wrap so that our texture coordinates will wrap if it goes out of bounds. And that'll be useful if we're using wrappable textures or wrappable scrolling background. For begin, we got a bunch of options here. We can use our regular draws, and we could draw to a destination. We could draw a full texture, which is kind of handy. So I could just say vector 2.0 to draw in the upper left-hand corner and specify a scale of 1f, because it's the same size of the screen anyway. And we'll try that out. All right, so now we got a background. It looks pretty good. I was thinking of making this into a vertical scrolling shooter, so maybe we'll rotate the background by 90 degrees so it's facing kind of up and down. I suppose it doesn't really matter much, but so I'll try using a regular draw call, and we'll set a source rectangle to just be the entire texture, and we'll put it at position vector 2.0. Okay, let's see here, and we can put it scale 1 and rotate it by like 1.57, which would be 90 degrees in radians, and color.white, 100% on all color channels. So when I run that, now it's vertical, which is more suitable, I think, if we're going to be scrolling vertically. So let's make a scroll vector that'll scroll the background using the Y of the scroll value. And what that's going to do is going to change the rectangle where it's going to get the image from, rather than changing the destination. So the destination will stay at 0, 0, but the source will keep moving, and it'll wrap in texture memory because we're using this linear wrap thing here. So to change the source Y value, we'll put a scroll value here. So I just changed the texture width height to just 1024/768 because I know that these are the same, and we're not going to change the resolution, so it's okay for me to do that. Here I added this scroll vector. It has to be cast to an integer. It'd be different if I used a point actually, but I want precision in how fast it moves, so I'm going to use a float instead. Let's just go up to our variables here, make sure we have a vector 2 set already that we're going to use called scroll. So let's go down to update, and right under this we'll add a scroll amount per frame for the far background, so it'll just keep continuously scrolling, and we'll try that out. So far so good. It doesn't look like the destination width is quite right, and that's probably because we're rotating this. Now we could also use a version that would take advantage of the destination or do some scaling. I think first what I might try is we'll switch to a 3D camera instead of the 2D camera that we would normally use and see how close to it is. So right here in quad we can say use 3D camera. It's true. We'll try that out. Okay, so it's still a little too narrow, so I'm just going to replace this with a scale vector 2. I suppose I could use rectangle destination too, but I'll just do it this way. So 1024 divided by 768 would be about 1.3, so we've got to scale it by what, 1.3, something like that. Try that. Oops. I forgot we rotated it, and the scaling happens first. So that could make things a little bit confusing with it being rotated. So we got to scale it the other way. That looks better. And how about we center that red a little bit better? So perhaps we'll set the scroll.x to some initial value. It should be 0, 0 automatically to start with. So we'll just set x to equal to, and we'll try 50, see what that gives us. Yeah, that's pretty close. Or maybe 70, 60 or 70 or something. Yeah, we'll go with 64, that seems to be fine. And I guess while we're here, let's go down to initialize and add in the shot coordinates. Oops, what happened there? New rectangle, I got 199, 7, 51, 49. We're gonna need to put a ship on the screen. Actually, first, let's add the middle background, and maybe even 2 layers that we can scroll at different speeds. I just realized too, if we're going to draw rectangles to diagnose where things are, and where the collision rectangles are, we'll need to add a quad.pixel value. This will set a rectangle, and I happen to know that one of the pixels in the boss at 223,31 is white, so we'll be able to make that any color we want. Oops, this should say new. It's fussy that way. So we've chosen a pixel that we can use to make our lines in quad. Let's go down to the draw method, and we'll add those other layers of background. But I think this time we'll use quad.begin, mid background. It's a different texture, and our blend state will be additive blended for the stars. We'll also use a sample state of linear wrap. By the way, you may be wondering why I put scroll Y in the X and scroll X in the Y. That's only because I rotated it 90 degrees, so that kind of messes things up, so I had to swap these two around. But normally the X would be here and the Y would be here. It's probably better if you don't have to rotate this, just rotate the graphical image and then save it as a new file, and then you don't have to add this rotation in there. It's an extra computation too, so it's just avoids confusion. But for this example, I'm just going to leave this as is, just not the way I'd recommend doing it. Okay, so I added this. I changed the scroll X to 1.5 and the scroll Y to 1.5, which is twice as fast. But everything else is the same, except there is no rotation on this one. So we don't have to have the X and the Y swap. And we're not doing any kind of backward scaling either. So this one's just straightforward. And this is what we get. And I'd like to add another layer to it to make it look a little more cool. So this line's exactly the same. I'm just going ×2. We'll see what that looks like now. Okay, so it looks pretty good, except I think the background that's further away should be a bit smaller, and so we don't have as much repetition. Maybe we'll flip it horizontally and vertically, so it'll look different. So we'll scale it smaller and flip it vertically and horizontally. First, I'll start off by changing the scale to 65% of the size. Now, the thing with doing that is you'll notice that it's not drawing all of it. Because it's 65% smaller, it's not filling the screen is what I mean. So we needed to draw an extra 35%. So we need to extract from the source for an extra 35%, and it'll wrap in memory, so it'll stretch it out, because we're using this linear wrap here. Because it's smaller, we got to extract more. Let's try just changing this to 2000 and this to 1000. We'll just be crazy and see what that does. Whoops, I modified the wrong ones. I want this one changed to 2000 and this one to 1000. We'll see how that looks. That looks a lot better. It still doesn't seem quite right. I think the far background looks like it's moving a bit too fast now, so perhaps what we should do is divide it by 2, so it's moving slower than that background. We'll do that on the X and the Y. There we go, that looks better. Maybe we could make the far background a little bit darker. We'll go with gray. We could change the color a little bit, maybe a light blue on this background, and see how that looks. Yeah, so the middle background's a little bluer and the background's a little darker. So for one of these backgrounds, we can add a flip flag. I'm going to say sprite effects flip, and I'm going to OR 2 of them together. So sprite effects dot flip horizontally, and merge that with sprite effects flip horizontally. Then over here, we can add that parameter, and that'll further vary this background, so it'll be more distinct from the closer background. Yeah, it looks better.